Great. Yeah, thank you. My name is Drew Jamieson. I am a postdoc at the Max Planck Institute for Astrophysics. And today I'm going to be talking about an emulator for large-scale structure, specifically a field-level emulator, which is built out of neural networks, styling neural networks. I'll describe what they are in a bit. This project began at the Flatiron Institute, CCA, where I was working. I was invited there by Shirley Ho. And since then, this has kind of grown into an ever-growing list of more collaborators at more institutes, and we have many different sort of projects going on. You can find the code for the results I'll present here at these GitHubs, and the papers that I'll present are here, as well as some new results that have not yet been published. So I'll begin by describing the idea. The idea is to train a neural network to learn the map from linear perturbation theory, from the Zeldovich approximation in Lagrangian space, to the nonlinear outcome of an n-body simulation. So essentially, you take the linear field you would use to set up the initial conditions for an n-body simulation, and you feed that through this neural network. Specifically, you've got 3 channels in the input. They correspond to the Cartesian components of the displacement field on this uniform Lagrangian grid. And the network has this UNet VNet design. So the UNet refers to the shape of the neural network, and the VNet refers to the fact that it's a volumetric network. It deals with voxels instead of the traditional pixels of image analysis. And so it passes through this 3D field of this vector field, this displacement field, and that undergoes a couple convolution operations, and then downsampling, and then convolution operations and downsampling, and then eventually convolution operations and upsampling until you get back to the original size, and then you output a 3D vector field. And what you're trying to learn is essentially, if this is the Zeldovich approximation for the field initially, and this is its final displacement after n-body evolution, you're trying to learn these residuals between linear theory and the nonlinear evolution. So one benefit of this kind of design is that based on the set of convolution operations and downsampling, upsampling operations you have this finite receptive field, which for one focal particle corresponds to about a size of 200-ish megaparsecs. And that's nice because on scales much larger than that, the evolution is linear. And so you preserve that linear mapping on those large scales, and you get the neural network to focus on the small scale, difficult problem of nonlinear evolution. So that's the model. And the question is, how do we incorporate cosmology dependence into this? Because we don't just want to train a neural network for a fixed cosmology. We want to be able to give it a set of initial conditions for any lambda CDM cosmology and get it to output the result of an n-body simulation. And the idea we used here is kind of an old one now in machine learning, but it's the idea of splitting up information into content versus style. For us, the style is the cosmology, and since we're doing n-body only, or dark matter only n-body simulations, the style is really just one parameter, which is omega matter. And what we want to know is how to transform the content into something else, which is the nonlinear field, but with a given style. And so the way that works in practice is that we have weights and biases of the neural network, but we also have these additional style parameters. So we map omega matter into an array of other parameters, and those modulate the weights and biases of the neural network before we pass any data through. And in that way, I've kind of augmented my neural network into a whole ensemble of neural networks, one for each different value of omega matter, and I can train them all in one go by feeding through a suite of simulations that span a range of cosmologies. And so what we're really doing is we're learning the nonlinear, the mapping from the linear to the nonlinear field in a way that dependent continuously or differentiably on this parameter omega matter. So to summarize, we're learning this linear to nonlinear mapping. We input the Zeldovich approximation, and we output the nonlinear displacement field after n-body evolution. The model evaluation, if I take, say, a cubic box of 128 particles cubed, we have to pad periodically the particles at the edge because of the receptive field. But if I pass all these particles through on a GPU, on one single GPU, it takes about 0.7 seconds to evaluate the model, so it's super fast. The number of parameters is somewhere around 3 million, and the number of style parameters is only about 5,000. So turning the neural network into a style neural network is not a big cost in terms of having lots and lots of parameters to train. The loss that we use when we train this has 2 parts to it. One is just a particle-wise displacement error, the mean squared error for all the displacements in the box. And we also, when we make our prediction, we construct an Eulerian mesh of the density field and also add that to the loss. That makes it train faster. It trains very slowly if you don't do this, actually. In fact, we really reweight these. We weight this one by a factor of 1/3, but it's kind of a technical detail. And then the training data that we use is the Quixote Latin hypercube set of simulations. So there's 2,000 simulations. We used about 1,700 of them, I think, for training, and then split the other set into validation and testing sets. We only test it on sets of simulations that it didn't see training. Each simulation has totally different random initial conditions and different cosmological parameters, which are sampled on quite a wide range of this 5-dimensional Latin hypercube. So then we train this for about 80 epochs, and we sort of publish the results in this paper here. And so here I'm just going to show the results for the density power spectrum. In this paper, we showed a lot of other statistics, but here I think we'll just focus on the density power spectrum now. So the density power spectrum and the momentum power spectrum. So really, we trained 2 models, one for the displacement field and one for the velocity field. And so from the displacement field, we can construct the nonlinear density field. Here on the top, we have the power spectrum. On the middle, we have this the stochasticity, so the error from cross correlation with the n-body simulation. And at the bottom, we have the transfer function errors. And we're comparing with COLA, which is a particle mesh algorithm that uses Lagrangian perturbation theory to do the time stepping. It uses like tens of time steps instead of, say, thousands that an n-body simulation uses. So it's a super fast simulator, but it's not very accurate on small scales. And so you can see that our errors are much better than COLA's in almost all cases. Our worst cases are cases where sigma 8, so the colors of the curve correspond to sigma 8. So sigma 8 being very high is very challenging for our models, but even in that case, we're basically just comparable to COLA. Specifically, actually, the very worst cases are ones where sigma 8 is high and omega matter is very low. And those are bad because omega matter being low actually increases the amplitude of the power spectrum. Sigma 8 being high increases the amplitude of the power spectrum. So what you're doing is you're making lots of halos. And when a particle goes inside of a halo, its trajectory becomes very complicated. And it's very difficult for the neural network to figure out exactly where on its orbit, inside of a halo, sort of virialized complicated motion, the particle is supposed to be. So the more halos you generate, the more difficult it is to figure out on small scales what actually is the fate of all these particles. And so similarly, we have the momentum power spectrum from the velocity model. The errors are, because this relies on the displacement field to construct the momentum field, the errors are a little worse because you also get error propagation from the errors in the displacement field. But again, we're doing much better than COLA for this range of cosmologies. Now, one question is, how serious is this sigma 8 error dependence? Is this the thing we need to really worry about? And I think we kind of answered that in a recent paper, which is by my collaborator, Marcos Ferreira, who's at the University of Edinburgh now, and Raul Angulo, myself, and Yun Li. And so what we did is we constructed this Lagrangian space hybrid bias model. And so we're treating galaxy fields as a sort of biased field in Lagrangian space. So we construct the galaxy field as a set of terms that are sort of operators acting on the linear density field, which is delta here, along with a bunch of bias parameters. So we're doing a bias expansion. And the idea is to then advect this Lagrangian space field to Eulerian space to get a mock for the galaxy field. And so normally you might do something like use an n-body simulation to do this advection. But here what we're doing is testing how well this map-to-map field level emulator does instead. And so this plot just shows the various power spectra and cross power spectra for these different operators from our mocks. Now, the way this relates to our sort of cosmological, specifically the sigma 8 dependence of the error, is that we really want to do this in redshift space. And the way we do this in redshift space is kind of model some of the aspects of redshift space using parameters. We parameterize the fraction of satellite galaxies, Fs, and we also parameterize the fingers of God effect. We also parameterize sort of a noise model for our Lagrangian space field, which corresponds to stochasticity of the small scale unmodeled physics below, say, the resolution that we set up the grid on. And we're going to sort of fit and marginalize over these nuisance parameters. Anyways, they model the really small scale physics that we have a lot of uncertainty over. And we're free to also allow those parameters to absorb some of the uncertainty in the emulator itself. And when we do that, it turns out that this sigma 8 dependence on the error goes away. So these plots are showing the difference between the power spectrum from map to map and the power spectrum in the n body, normalized by the variance of the mode. And here, the mode that we're looking at is k equals 0.6 inverse megaparsecs, which is kind of the scale at which we expect the Lagrangian bias model to start to break down. But we see that when we allow these parameters to absorb some of that cosmological dependence, the error dependence on sigma 8 goes away, and we no longer have this sort of strong dependence on the error of sigma 8, which I think is kind of comforting, because this is something we're typically going to have to do anyways, marginalize over nuisance parameters that parameterize uncertainty in really small scale physics. Okay, so another question we try to answer is this thing actually learning physics? Which is kind of a cool question. And so the way we test this is very hard to interrogate a neural network and ask it what it has learned. But we can set up scenarios where we know what the answer is, but it has never seen anything like this before. So an example is a perfectly spherical configuration. The only thing it's ever seen is just random Gaussian fields. So there's nothing random nor Gaussian about a spherical top hat. And so if we set up a spherical top hat, either over density or under density, we know analytically how it evolves. So we can ask, does the neural network know how it evolves? And in fact, it basically does. There's one small caveat, which is that if you compute what this is the linear overdensity we set up versus the non-linear overdensity that it ended up with. And so this is like the analytic curve that you can just calculate for spherical evolution. If you take the very edge of the top hat, the sort of finite resolution effects fuzz out that edge. And so you do get some errors, which are these blue curve you see here. It's the prediction you get from the neural network. But if you just exclude a small shell at the very edge of the overdensity or underdensity, then that fuzzy region is excluded, and it very, very, very closely matches the spherical evolution. So it's impressive. It's never seen anything like this before, but it knows how a spherical top hat evolves. Similarly, we set up systems where just two modes were excited. So we take one mode in one direction, one mode in the other direction, and we allow them to couple together through nonlinear gravitational evolution, and they should generate a pattern of modes, a pattern of amplitudes and phases. And that's what this shows here, is the pattern of mode amplitudes for various different modes after evolution from the simulation and from the neural network. And again, it knows how mode coupling works. It knows how these two waves interact together to generate other waves under gravitational evolution. So I think this is kind of somewhat convincing that it has learned, it has encoded information that is somehow related to the underlying physics that we're trying to model. Okay, another question is, can we do the opposite? Can we learn the initial conditions? And so this is a project that was done by this master's student. They have Jindal, who trained the network by replacing the output and input. And what we find is, yes, it basically performs just as well as the forward model and recovers a field that is very close to Gaussian. So I think I was a little surprised by this. I thought this wouldn't work so well, but it's actually, it works pretty well. I should say this is like a long way away from doing actual like reconstruction, because this isn't in redshift space, and this is, so there's a lot of caveats here, but still, I think it's impressive that it's able to kind of recover the linear field from the nonlinear field. So then the final thing that I want to talk about is the new thing, which is adding the redshift dependence. So how do we add the redshift dependence? Well, the same way we added the cosmological dependence. We just give it more style parameters. And specifically, I gave it style parameters that map the linear growth factor as a function of redshift to a bunch of parameters that modulate the weights and biases based on what cosmology you're in and what redshift you want to map the linear field to. And this works so well, it's almost boring to talk about. It's just like, it works really, really well. This is power spectrum, again, stochasticities and errors in the transfer functions. At earlier redshift, it's way easier to learn the map. So I should say, we start with the original parameters from the trained neural network at redshift 0, which is the hardest part of the map to learn when things are the most nonlinear. And then we train from there, which is kind of sort of like transfer learning. And from just like 12 extra epochs of training, it's basically gets this great result. And it's way, way better at all the early redshifts because it's an easier map to learn. It's less nonlinear. But there's actually huge advantage here. The huge advantage is that we no longer need a separate model for the velocities. because, and it took me an embarrassingly long time to figure this out, but velocity is just the time derivative of displacement. And a mind-blowing stuff here, but but we can compute the forward derivative through the model with respect to, well, the linear growth factor first, but then we know how that evolves with time. And then we get the velocities for free. I should say, to be fair to myself, this was actually not possible like a few years ago because all the machine learning kind of infrastructure was based on computing backward derivatives for back propagation to train networks. And there weren't really good, highly optimized algorithms for computing the forward gradient, even though it's not a harder problem. But recently that's changed. And so I added the velocities, but I can evaluate those velocities during training and then add them to the loss, which means I'm training on the full phase space of the trajectories of these n-body particles, which is like a huge improvement on the constraints of the training. And then, so basically I train that for, I don't know, 6 epochs only, and I get these results. So these results are for a sample of cosmologies. The ones on the sides are the extreme corners of the Latin hypercube. So high omega matter, low omega matter, high sigma 8, low sigma 8. And then the middle one shows the fiducial cosmology. So again, the errors are extremely good, but the kind of cool thing is that I'm showing as the white dashed curve the original model. And there's a huge improvement, especially for the velocities, in the accuracy of this, from just training only on the displacement field, but giving it information about how the time derivatives of those displacement fields should also observe. So training on the full phase space all at once. So yeah, so this is a very sort of successful way to augment this model with redshift dependence. In conclusion, we have this like very fast and accurate emulator for basically n-body simulations, which is extremely accurate down to deeply nonlinear regimes. It's differentiable. It can be used to sample over cosmologies and initial conditions. Currently, I'm collaborating with some people in the Borg group, which they do this Hamiltonian Monte Carlo sampling, and they're testing this out with their stuff. And I'm not allowed to talk too much about that, but it's I think some cool results coming out of that soon. And so we can really do, we can really start to build a sort of field level analysis from these kinds of emulators. They model this full phase space of the n-body evolution, and now we've added this redshift dependence. Sort of the outlook is that we can consider augmenting this with more cosmological parameters. We don't need to consider things like FNL, which only affect the initial conditions, because it already knows how to do that, because the late time gravitational clustering doesn't depend on that. But things like, say, curvature or massive neutrinos or equation of state for dynamical dark energy, those affect the late time gravitational clustering. Also increasing resolution, baryons, and now I'm trying to get light cones out of this too. So there's lots of work to be done. Thank you.